Chapter 20 is about expression-oriented programming, or EOP. And this is a really important topic, so I really want to expand on it much more than what I show in the book. So the first thing you need to know is the difference between statements and expressions, which I show in this section here. And the first thing is that a statement is a block of code that does not return a result, and it's used solely for its side effect. So the typical example here is print line. Print line is used for its side effect. You're just printing something to standard out and you don't care about its result. So basically what you do, you don't say val x equals print line whatever, right? Because that doesn't matter. You don't assign the result of print line to any variable because you don't care about the result. You're just printing something to standard out and that's it. So you don't care about the return or the return type. So that's typically what statements are. They're used for side effects, and side effects are things like printing to the output, reading input, and mutating state somewhere within your application. So when I say reading and writing, that could be the file system, that could be a database, could be anything on the internet. So all of those things like reading, writing, and mutating state, those are all side effects. And now almost the opposite of a statement is an expression. An expression is some block of code and it returns a result, and it typically has no side effects. The reason this lesson follows the previous one on the if-then expression is because if-then returns a result. And I show that in this next section here. So I have an if-then expression right here, and it returns a result. This returns basically the min of A and B. So what happens in EOP, expression-oriented programming, is you have an expression on the right side of the equal sign, and then that expression is assigned to a variable on the left side of the equal sign. And an important part about things like this being expressions is that makes it really easy to write methods. I can show this in the REPL a little bit better, that you can write a min method. Even though I haven't gotten into methods yet, I could show if you want to find the minimum of two integers, you would pass those two integers into your function. So I would pass in parameter I, which is an int. I'll pass in j, which is also an int. And because I'm finding the minimum of two integers, then this is also going to return an integer. So I have that as a return type equals. And again, the way this ties in is because it has to do with the if expression. So now I could say I want the minimum. So if I is less than j, then return I, else j. All right, so that will give me the min. So just to test that, 1 comma 2 gives me 1, and then 2 comma 1 should give me 1 as well, and then 1 comma 1 should also work. Again, the key here is that this is an expression. It returns a result, or we actually in functional programming, you would say this evaluates to a result, and then that result is returned from this function here. I'm kind of jumping ahead here, but I want to note that this is a pure function. So part of what I mean by that is everything this function needs is passed in between this open and closing brace. Right, there's no side door, so there's nothing else that comes into the body. Or to state it another way, here's the body of the function. And even if this was many lines long, if you look at every variable here, every variable that comes in from the outside world needs to come in through this front door right here. I refer to that as a front door. So I and j come in through here, and they're used in here. There's no magic. There's no K or anything else that comes in here. I don't print anything. I don't read anything. I just work with the variables that I'm given to return a result. And because this is such an important topic, I want to get into it more with one of my other books. This one's called Functional Programming Simplified. Of course, it talks about functional programming, and expression-oriented programming is kind of one of those things that leads into functional programming. And as I roll along, where am I? There's the expression-oriented one. So kind of an important thing I need to note here too is that I talk about pure functions for several chapters here until I get to expression-oriented programming. So now you can think your entire world at this point consists of pure functions. And again, in this chapter, I make it clear what statements and expressions are. I do a little bit better job here because I don't care about the size of this book. This one's over 700 pages long, so I can write everything I want to. Whereas the Learn Scala 3 Fast book I was trying to keep very small and with very short lessons. I kind of reverse things here and say that an expression has this form. So you have a pure function, you have some immutable values. It can be as many parameters going in the front door here as you need. And then this pure function works with those immutable values in your algorithm, and it returns a result, and you assign that result to a variable. That's the way expression-oriented programming looks. You just have a bunch of expressions like this, one line after another, after another, after another. Now you can contrast this with the object-oriented programming code or statement-oriented code that I used to write 15, 20 years ago. And I need to mention too, my background was aerospace engineering. I didn't have any computer science classes, so I didn't know anything about the difference between statements and expressions. So in Java, I just wrote everything as object-oriented code, and it used to look like this. So I would have something like an order object, which is like the order you would have at a pizza store or any other anywhere else. Like you go to any store, you create an order. It consists of line items and products and so forth. And so then the way we were taught in object-oriented programming was you would create a method, or you create many methods on an order to do different things. So I have an order, and one of the things I need to do is calculate taxes. And now this code looks really, really weird to me because I look at these open parentheses here and I'm going, ooh, something's really wrong. Well, I look at two things here and I'm thinking something's wrong. I look at those parentheses and nothing's coming in these parentheses. And I'm like, something weird's going on, right? Because nothing's coming in the front door. This means everything's coming in and out of some back doors and side doors. So I have no idea what this does. Fortunately, it has a meaningful name, so I can tell that it's calculating taxes. So all I can tell is that it's using stuff inside the order and it's using some other stuff. Somehow it's calculating taxes and then it's putting those taxes somewhere else. And I have no idea where that is. I mean, I don't want to go too crazy, but honestly, if you look at the code, you have no idea what's going on. And then it doesn't return anything. So that's the second thing. The first thing was there's nothing coming in the front door. And then the second thing is I don't see val something equals something here. So this is totally side effects going on here. Calculations are going on, but who knows where anything goes, what it's using. This one actually is a little bit worse because the name is a little less meaningful. So I look at that code, nothing coming in the front door, no result. Right. So again, those are statements. Those two are statements. They don't have a return value, and who knows what's going on, just a bunch of side effects. Conversely, in functional programming and EOP, and we don't even have to get into functional programming, we just say in EOP, we would write these as expressions. So I could still have an order object, but it's immutable. And then this is a pure function, calculate tax. So the order object comes in the front door, calculate tax works with that order, it doesn't mutate it, and then it returns a result, which is the tax on that order. And similarly, calculate price takes an order coming in the front door, does whatever, doesn't mutate that, does whatever it needs to calculate the price, then returns the result, which is assigned to this variable here. And these are expressions. And I oversimplified things here a little bit because, if you've ever written code like this to calculate a tax on an order, you didn't need the order, but you also need to know information like the city and state, and maybe there could be other local taxes as well. So those would also be coming in what I call the front door. So they'd be coming in right here. So you'd have order, information about the city and the state. You might even have a tax calculator come in this front door, and then that would return this result, which is the tax on this order. And then I write here, while that might seem like a minor change, the effect on your overall coding style is huge. This sort of code, the expressions or expression-oriented code, makes your life so much easier in the testing world. Well, it makes your life easier in several different ways. It makes your life easier when you're writing the code because all you have to worry about is this local universe. You don't have to worry about what's going on in the entire state of the entire application. Like, are you mutating state over here? And is that mutation here affecting some code over here? This is your whole universe right here. This function and everything that's coming in the front door, and then what you're returning right here. That is your entire universe. It's the only thing you have to think about when you're writing expression-oriented code and functional code. And that is so much easier. So it's easier to write the code. It's easier to read this code because you know that all you have to do is worry about front door, what's coming out. And then it makes your code so much easier to test because you can see in your tests, I wish I had that set up here, but basically you would have a couple of lines of setup. You would say, here's my line items, here's my order, this is the state that I live in and the city, and then you would pass all those things in right here. and then the result would be here, and then you just test this result. And again, you don't have to worry about the order being mutated or wherever the taxes are being mutated within this order object. The only tax is right here. You don't have to mutate anything here, and then you don't have to dig into that object to find that mutated thing. So now a key point here is when I look at this code, these are two statements, and that code looks really, really weird because there's nothing going in the front door in these parentheses, and there's no result coming out of these. So I'm like, these are statements, there's some side effects going on. Who knows what those are? Then for the purposes of this lesson in Learn Scala 3 the fast way, two important things are if is an expression and it returns a result. I know that, and this is, I need to note that this is the Scala 2 style, but if is an expression and it returns a result. Match is an expression that returns a result. So you see them being assigned to variables here. And even try catch blocks are expressions that return a result. So I show that in toInt method here, again, Scala 2 style, but try catch returns a result, which is an integer. I make sure it's an int in both cases. And now I want to continue down this road just a little bit longer. And the way I do this in my functional programming book is I say, I've got this next lesson, functional programming is like Unix pipelines. And if you know Unix, you know that you have commands, and then you can pipe the output of a command into another command, and then you can pipe that output into another command, and so on and so forth. So I show how that works in this lesson. So your boss comes to you and says, I need a script that will tell me how many unique users are logged into a Unix system at any given time. So he wants number of users, but he wants number of unique users. If you know Unix, you know that you start with the who command, and then the who command gives you this output, which is well-structured, it's consistent. The approach that I stress in functional programming, simplified, is that you always want to have an algorithm. And sometimes I'll sketch down the algorithm. If it's short, you can do it in your head, but if it's longer, you might want to write it down. So here I sketch it out just to be clear. So I think the algorithm is that I want to run the who command. It gives me a list of, I can get a list of usernames from that first column of output right here. And then I need to get only the unique usernames from that list, and then I can count the resulting size of that list. The Unix world, that translates to chaining these commands together with pipes. So I start with who, I pipe that into the cut command, then I need to use a unique command in wc-l to count those. So I start with who, then I pipe the output of who into the cut command. Basically, this just gives me the first field of output from the who command, which is the names of these users. So now my current pipeline returns this list of users, and you can notice here that the users are not unique. So I need to make those unique. And the way you do that in Unix is you pipe the first result or the second result into the unique command. And so unique transforms that. So now I just have a list of unique users. Again, the goal was to get the number of unique users. So then I pass that result into wc-l, which is a line count. That gives me this output, which is number 3. And initially, when I started writing this, I thought I would be done. And then I was like, oh my gosh, it has these leading characters here. So I wasn't counting on that. So that's where your algorithm has to be flexible. And I guess your mind has to be flexible too, right? So then I pipe the output of the wc-l command into this tr command, which basically deletes all those leading characters. And this finally gives me the result that I want. But that's how I do it in Unix. So next thing I show is how I would write this as a shell script. And note that each one of these is an expression. So you start with the who command. This is kind of like a is this a function. It does reach out in the outside world, and it, depending on how you want to look at it, either returns a multi-line string or it returns a string as a sequence of strings. And then I proceed with 4 what I would call expressions here with res1 through res4, and then I echo out the result here. And then I do exactly that. I kind of translate that to Scala. So I'd say I've got an expression here. So I assign this. Get users is some function. I call it an impure function because it reaches out in the outside world. It gets its result. And then I say that result is a sequence of strings. And then if I were to go through and write these other things, these would all be pure functions right here. So cut takes this who output, and it takes these other 2 parameters, and it returns a result. I take that res1, pass it into unique, so I get the unique usernames, and I return that into res2. I pass that into count lines, which gives me a count of those unique users, and I make that res3, and then I pass that into trim, which I don't really need in the Scala code, but I did need up here, so I just kind of Trying to make that similar. And then down here, you would have the print line, which again is a statement, and this is your results. So this is what you want to show your boss, is the number of unique users. And now I want to show you, this is the cool thing that I totally did not understand like 15 years ago. So if everything you have is an expression, everything is immutable, everything is pure functions, you can do what I'm about to show you here. So what I just showed above was you have these well, actually 5 expressions. I skipped the first one here. And what this leads to is you look at that code and you go, well, you know what? I passed res1 in to unique right here. And because cut is a pure function and because everything is immutable, res1 is exactly equal to this. So I can go ahead and get rid of res1 and I can just put cut inside of here. And that helps me eliminate res1, and now I just have these other 3 variables. And then I continue along the same line of reasoning, and I say because res2 is equivalent to the right side of its expression here, I can eliminate res2 as an intermediate value, and then I can just plug in, I can take this code right here and plug it in replacement of res2 right here. And then I get this code here. And then I eliminate res3 for the same reason, because res3 is exactly equal to this and will always be exactly equal to that because I only use pure functions and immutable values. So I can get rid of res3 here, pass this into trim, and I get this code. And now you can I could just say print line res4 like I do here, or how I did originally. But now I could actually just do this. I could say print line this combination of pure functions. And I always mention this makes my code feel like Lisp because you end up reading it from the inside out. So you'd say get users like that, and then apply cut to that result, then apply unique to that result, apply count lines to that result, apply trim to that result, and then print it. And because I have those attributes, I can take this code that I start with initially, and if I want to, I can make it look like this. There's nothing in the world that says you have to make it look like this, so you can always leave the code like this if you want, but if you want to, you can also make it look like this. And then kind of as more of a bonus on the next page is I get into some drawings here to help show this. So basically you have the who command is a source of data, and it gives you a data stream, which again, you can think of as a multi-line string or a sequence of strings. Pass that into a cut function, which is a pure function, takes this input, returns another sequence of strings, pass that into a unique function. So this is, again, this data comes in the front door, comes out the back door, nothing comes in the side doors. Then this data here, the sequence of string comes into unique, it works on it, and it returns another sequence of strings. That goes into WC, again, front door, back door, front door, back door, no side doors. Cut, unique, WC, and TR are all pure functions, and you can think of those as transformer functions if you want. And then on the page after that, I start getting into our example, and I show visually, I hope you like my hand drawings here, but I show visually how that works. And when I can get into all that, you can read this book if you'd like. And again, this is all in my other book. This one is called Functional Programming Simplified. Okay, so I got a little carried away there, but in summary, this was a video version of chapter 20 from my book, Learn Scala 3 the Fast Way. And again, this chapter was on expression-oriented programming, and I showed other examples from my other book, Functional Programming Simplified. My name is Alvin Alexander, and I hope you enjoyed this. Thanks for watching.